homework 5. Homework 5 was good. Good morning. Yeah, all of you need coffee, including me. So, what I have decided today is I'll do a question on second order systems first, then I'll present the data regarding a standard aircraft, the Navion aircraft, which has been used in multiple homeworks. And then I'll do 5 questions, 2 in this session and 3 in the afternoon one. So go and watch the 3. And anyone wants to take a guess why 5 questions on a Navion aircraft?
The 5 nodes.
Yep. Short period, long period, spiral, roll, and Dutch mode. And you will be, and I have designed the questions yesterday night in such a manner that it covers like basically going and finding out the eigenvalues and eigenvectors of each mode, as well as developing a stability augmentation system for each of the modes. But then you also have something called coupling in lateral modes. And also there's the concept of if you create a reduced order model, like for example in short period mode, you assume that the change in forward speed is almost negligible. So we drop 2 equations of motion and we only look at theta and q. So W and Q, sorry. So it turns out that it's not exactly an accurate model if you would simulate the entire 4x4 system and if you would simulate the 2x2 system. You are aware of this, right? So while designing a stability augmentation system, you have to take care of this, and you have to acknowledge that, if I am designing a stability augmentation system based on feedback loop for a reduced order model, it may not perform exactly as intended for the original model. So before you fall asleep, let's move on. So the first question that we are going to discuss today is, so let's again consider, so this question I'm doing just so that you have an idea of what would be asked from a second order system, everything that could be asked from a second order system. So again, consider the same thing that you have a wind tunnel and I have a strut, and we have fixed an aircraft with you can say some kind of, I shouldn't say damping. So now this has both we have elevator control here now, and we have switched on the wind tunnel, and we can assume that delta U is 0 and only pitching is allowed. So you are already provided that theta double dot plus 4 theta dot plus 16 theta equals 32 delta t. This is the equation of motion. So if I had a very silly question like, can you give me the damping stability derivative for this equation? What would it be? 4 or minus 4? Minus 4. Okay. So be cautious about that. The original equation is theta double dot minus, so it's theta double dot minus mq theta dot minus m alpha. Yes, theta equals m delta e as a function of time. Okay. So be cautious about this. Now basically what you can be asked is 3 kinds of things. First is I could ask you to go ahead and, let's say I'm asking you determine the transfer function, identify the natural frequency and damping ratio, and tell me if the system is critically damped, over damped or under damped, right? So what is the transfer function? Transfer function is basically, it is the Laplace transform of the output, which is theta, divided by the input, which is delta s. So how do we go and find these out? We go and take the Laplace transform of the differential equation that we have. So it becomes s square theta s for theta double dot plus 4s theta s plus equals 32 delta s. So is there an implicit assumption I am making while I wrote this Laplace transform? There is an implicit assumption I am making that I have been given theta dot and theta at time. Implicit assumption that I am making is theta dot at 0 and theta at time 0 is 0. Because remember that the Laplace transform of, let's say, x double dot is going to be s square minus s x at t0 x dot at t0 minus x at 0. Okay, this is the complete expansion of Laplace transform. So usually if you are not provided the initial condition, feel free to assume 0 and don't ask me during the final exam that the initial condition is not given, what should I do? So if it is not given, then simply assume that it is equals to 0. Now I have the Laplace transform. All I need to do is take theta as common on one side, and I would get s square plus 4s plus 16. Another side would be 32 delta s. Now Laplace transform has given you the Laplace transform, the frequency domain of the input and the output, and be cautious while identifying the input and the output. So output is theta s and it needs to be divided by input, which is going to be 32 over s square plus 4s plus 16. So the first part of determining the transfer function from the equation of motion is done. The next part of the question says identify the natural frequency and damping ratio. So it's straightforward. We have seen that if you go ahead and write down the second order, the transfer function of a second order ODE, you are always going to get something like s square plus 2 zeta omega n s plus omega n square as, I shouldn't say equal 0, but you would get this in the denominator. And now you have s square plus 4s plus 16 in the denominator, which means that 2 zeta omega n is equals 4 and omega n square equals 16. This should give you, I think, omega n as 4 and zeta as 0.5. Okay. Now once you have zeta 0.5, tell me whether it's underdamped, critically damped, or overdamped. It's underdamped. It's underdamped, which means that I can already predict the kind of response it is going to give. Why? Because if I give it some kind of input or some kind of, let's say, step disturbance, I am probably, this is not accurate, but it is very easy to draw this. So let's say I give it a step input, let's say 1 degree of delta E. So what happens to theta? It would go up something like this. Why? Because it's underdamped. If it were critically damped, you would have seen. If it were overdamped, you would have seen this. Okay.
So why is it underdamped?
So if zeta is exactly equal to 1, it's critically damped. If zeta is greater than 1, then it's overdamped. If zeta is less than 1 and more than 0, it's underdamped. Okay. So, yep. The next part of the question says, based on the location of the poles in the S-plane, determine the stability of the system. Okay, so let's go ahead and do that. I'm not going to do the math, but if you simply go ahead and compute the poles, all you need to do is you need to take the denominator of the transfer function, set it equals to 0, and then find the roots. You will see that the roots come out to be -2 plus minus iota 3.46. So the real part of the roots is -2 and we have a non-zero imaginary part. What does this tell you about the response of the system? What does the real part tell you about the response of the system? If it will, it's not stable, but yeah, I wouldn't say, yes, if it's stable, yes, if it doesn't blow up, correct. And what does the imaginary part tell you?
Oscillation.
Yes, it means that it will stabilize, go to a steady state value, but not directly. There will be some overshoot, right? Which means that this confirms, like, you did not need to go ahead and find out the poles of the system to go and guess this. We guessed the nature of the response before going and finding out the poles just based on zeta. So all you need to determine whether a system is going to blow up or not blow up, it's just based on the viscous damper. Okay. So this is just a review so that in case you get stuck in some questions, you can approach the same thing using multiple directions and make sure that what you're doing is correct. Now next thing is to basically, I put in this part of the question to make sure that you have all of this stuff in your cheat sheet, and on the record for the video, please do not forget to bring a cheat sheet. I can't have spare cheat sheets in a final exam. So what you are going to basically, I'm not going to solve this or something, but what I wanted you to remember is there are 4 very important things. 3 things you'll find in the notes. One thing is like an extra from my side because I think it's equally important. The 3 things that you'll find in the notes are basically the peak time. Peak time is the time at which the peak occurs, the first overshoot or the maximum overshoot. Okay, and peak time is given as pi over omega t. Omega d is the driving frequency, which is not the same as the natural frequency. And what is the relation between natural frequency and driving frequency? I think 1 minus zeta square. Yep. Anyone has any doubts? What happens if zeta is greater than 1?
So we're done.
It's overdamped, so there is no peak time. Okay, don't write an answer called there is an imaginary peak time, right? If it is overdamped, which means there is no oscillation, there is no overshoot, so there is no peak time. Hence peak time is only defined for responses which have zeta less than 1, not even equal to 1. Even for equal to 1, I showed you that you are going to get a response which is going to be something like this. It's never going to overshoot beyond the steady state value. It's going to very smoothly reach there. And if it's overdamped, it's going to just take a very long time. Okay. Next, that should be in your cheat sheet is percentage overshoot or POS. And this is given by exponential of minus pi zeta divided by root over 1 minus zeta square. So I will just write down, if you go ahead and calculate the peak time for this specific problem, it will come out to be 0.91 seconds. And if you compute the percentage overshoot, it comes out to be 16.3%. What does this mean? That this time point in the graph is approximately 0.9 seconds. And if I had given a 1 degree input, then the peak overshoot is going to be 1.163 degrees. Okay. Next thing is settling time. So remember that this formula of settling time 4 over zeta omega n, this is based on something called the 2% criterion. 2% criterion means if I had given a step input of 1 degrees, then 2% criterion means that when does the system attain 0.98 degrees and does not go below that, only keeps going towards 1 degrees. So it's going to be some point like here. So this is going to be your, like, when it has settled into the steady state value almost by 2% error. So this is going to be approximately 2 seconds if you calculate it for this problem. Like, you can go ahead and do all this math just as practice. I'm giving you the answers out. I usually don't do the arithmetic, but today is a final review, so I'm also putting down the answers so that you can go ahead and check. And something that is, I think, kind of makes sense and is usually not taught as a part, but also you can just for if you are curious, there is something called rise time. So rise time is given as actually we can skip that, no need to worry about rise time. So is this clear to everyone?
Can you repeat what the percentage overshoot is?
Pardon?
Can you repeat what the percentage overshoot is?
Oh, percentage overshoot is, so this is your steady state value, which would mostly be given with a subscript SS, and then this is the peak that your system attains. This is the overshoot. This was not desired, you don't want to go, but the system behaves that way because it's underdamped. So, like, if you have a system which has a percentage overshoot of 10%, 20%, fine, but you can actually come up with a system which has a percentage overshoot of 200%. So you're definitely going to destroy your system by the time it settles down. Okay. So this board here should act as, like, if you get stuck anywhere in a second order system, be its equation of motion, be its transfer function, be it finding the response, be it finding the poles, whether it is stable, unstable, and what is the peak time, what is the rise time, what is the percentage overshoot, what is the settling time. And remember that peak time is only defined for underdamped systems. It's not defined for critically damped and overdamped systems. So percentage overshoot and peak time, percentage overshoot and peak time, yeah, are only defined for underdamped systems. So if you get stuck, you should, like, this map should be in your head, that how is the Laplace transform related to the equation, how is the denominator exactly the characteristic polynomial. If I have the denominator, I can go ahead and find the poles, I can comment on the stability and stuff like that. Okay, now since we have reviewed a second order system in great detail, let's go ahead and start the second part of today's review, which is going to be, so I'll share the question, like, in the evening when I post the videos on YouTube. I'll not post solutions, go ahead and watch the video, but I'll write down the questions. So I've provided you with the derivatives of the longitudinal and lateral derivatives for Navion aircraft, and let's go and jump into the question, like, straight ahead. Give me a sec. Yep. So it's saying, so let's go like one by one. So again, each question that you will see has 4 objectives. First of all, you go ahead and find out the reduced order approximation of the mode. Then you go ahead and assess the flying qualities, whether it's in some kind of certain desired flying qualities, whether we can make it better. Then I have tried to come up with some reasonable values to go ahead and design a stability augmentation system for it. Finally, I do ask you to the question to just go and contemplate that whether the stability augmentation system that you have designed is going to affect other modes or not, because the modes are you're coming up with a reduced order model that's from a 4x4 system which is coupled, and then you're saying that you're making some assumptions that for example in the short period mode you're making the assumption that the variation in forward speed is 0. So that is why like two equations of motion go away and we are only concerned with W and Q. So what happens if delta U is not 0? How is it going to, like, it's very weakly coupled, the short period and long period, but the coupling in touch mode and spiral mode is not weak, as you'll see in lateral modes. So keep this in mind. I mean, it probably won't be like a part of the mathematical aspect, but all of you know that there is going to be a conceptual part in your final term. So yeah. Okay. So it's saying that like when you'll finally go and do the practice later on at home, you'll get all the values. Assume that all the longitudinal and lateral derivatives for the Navion aircraft is given, and then we are being asked, the first thing that we are being asked, so this is like short period stuff. So using the short period approximation, assuming that delta U is 0, construct the 2 cross 2 state matrix A short period, calculate the open loop eigenvalues, the natural frequency omega n SP, and damping ratio. So what is it asking? So our goal is here to find in the first part A short period, which is the system matrix, omega n short period, zeta short period, as well as open loop eigenvalues. Okay, so first of all, like, we need to construct the state space model for the second order system. So, and you should kind of have the entire thing in your cheat sheet. If you just have the 4x4 model, you can easily construct the 2x2. So I wouldn't like recommend against populating the 2x2 separately and 4x4 separately. It's just going to confuse you up. So obviously my state vector is going to be alpha and Q. And you can go ahead and look at your cheat sheet to come up with okay. The worst that we can make this question for you is to go ahead and compute one of these explicitly, like MQ, M alpha dot, something like that. For that, you should review the last discussion videos before Thanksgiving, where we did 2 examples in discussion regarding how to go ahead and estimate stability derivatives. But I am not reviewing linearization and stability derivatives and Euler angles. So it's your responsibility to go and review, because post midterm it's heavy content. So assume that all of this is given to you. So it's very straightforward. So if you look at the values, you can go ahead and do it. Another thing that I have kind of tried to actually do here is I have actually provided the relations for, so you don't have M alpha, so you don't have like M alpha is not given to you. M alpha dot and everything else is given to you. But what is given to you is MW. How are you going to convert it to M alpha?
Divide by U0.
Yep. Okay. So remember all of these things, that what is alpha? U by U naught. What is beta? V by U naught. Okay. So all of these things, you should recall that if some stability derivative is not given, if you need something as M alpha or M dub and the opposite one is given, then you can convert it. Okay. Just a small minor thing. Now if you go ahead and plug in the values that you will see later on while practicing, so just for the sake of continuing this conversation, it comes out to be negative 0.2, negative 7.02. Now, how do you go ahead and find the natural frequency and damping ratio? Come on.
Eigenvalues.
Huh?
Eigenvalues.
Eigenvalues. Okay. You go ahead and form the something called the characteristic equation. Characteristic equation is nothing but determinant of S times I minus SP. So you're just taking the determinant of S times I means S plus 2.02 minus 1 7.02 S 2.93, and you equate this determinant equals 0. Okay. Now if you go ahead and equate this, you will get the equation as S square plus 4.95 S plus 12.94 equals 0. So no surprise, every second order ODE is going to have this characteristic equation, and after this it's a walk in the park. Don't get excited and do the calculations properly, because a lot of you make mistakes. I don't know why. If you simply go ahead, omega n is going to be square root of 12.94, which is going to be approximately 3.6. Now tell me, should I give you full score for this? Why? What's your name?
But you still need to get your damping ratio as well.
No. Yeah, I mean that's correct, but
I think it's lambda, the units.
yes. Okay. Because in the midterm, the first question, a lot of you did it absolutely fine, but there were only 3 people in the entire class who got the exact answers that I was looking for, either in terms of degrees or radians. So all of you did it right, but I could see that you did not convert from degree to radians, or something got messed up. So always write this, okay? And and damping ratio is nothing but a constant, so it's going to be come out as approximately 0.7. Okay. Now the next part of the question, so we are kind of done with first part of the question. Okay, you can call it like part A. So part A is, my target was that you should be able to, what is the target here? That you should be able to go ahead and look at the 4x4 system, how to extract the 2x2 system from there, which is very simple and straightforward. Go ahead and look for the stability derivatives, construct the system matrix. If you have forgotten or are not confident about estimating stability derivatives, go and watch the discussion video before Thanksgiving. And then finally, it's very straightforward to compute the natural frequency and the damping ratio for the period once you have the 2x2 approximation. Now, the second part of the question says consult the level 1 requirements, which is the Cooper-Harper one given in lecture 16 notes. For each period, you have the flying qualities mentioned. No need to write down the flying quality data in your cheat sheet. It's a handbook. We'll provide you if it is required. Okay, we don't expect you to remember flying quality numbers. So no need to write it in your cheat sheets. It's going to take up enormous amount of space and it's going to be useless. So if we want you to solve a question regarding a specific mode, the flying qualities of that specific mode will be given there. So all you are required is to understand and have the brain power to look at that table and extract the information which you require. Remember that what will not be there is what is category A and C. What is category B? Is level 1 better than level 2, or is it the other way around? Okay. So only the information will be there. You just need to learn how to interpret the table. So consult the level 1 requirements for a class 1 aircraft in flight phase category B. Does the open loop aircraft meet level 1 requirements? So if you go ahead and look at the like the second part, a very small part, then zeta short period for like type 1 class 1 phase B is the range is 0.3 to 2.0. So zeta is actually like perfectly within the range and actually towards the lower value. So it's a class 1 aircraft for phase B operations. What are phase B operations? Non-terminal civil. Okay. Non-terminal military A, non-terminal civil B, terminal C. Okay. And level 1 is better than level 2 is better than level 3. Okay, not the other way around. Next is, so yeah, now we will go ahead and do the stability augmentation system part. So we wish to design a pitch rate damper using the state feedback, and the control law is given to you as this. Okay, if the control law was not given, what would be the control law that you should have assumed? So here I am explicitly giving you the control law. If I just wrote that we are going to design a feedback controller,
U tilde is minus K1 X1 minus
what is x1? Alpha.
Q.
Okay, yeah. So here I am explicitly telling you that the feedback controller does not depend on alpha, it only depends on Q. But if it were not given, you would have to find both K1 and K2. If the control derivative is given, let's say that m delta E is given as negative 5 per second square, determine the gain kq required to increase the damping ratio. So the damping ratio desired is going to be 0.7. Okay, so how are we going to tackle this? We are going to basically say that where did it go? Yep. So what's going to happen when you have a control loop? So now you have basically earlier what was your where did it go? Yep. So where yep. So what term is it going to modify?
The S term?
S term. Why?
Because that's the only one with zeta.
Because it is the only, because my feedback only affects the Q term. Okay, and Q term is only going to be the part that, or the coefficient that stands with the S term. So if you go ahead and look at the coefficient of the S term, so the only thing that's, so it's like the only thing that's going to get disturbed is the MQ term. And MQ, when you like bring M delta E from the other side, so remember that you will have a second order system which would be equals to M delta E times delta E, and then delta E is given as KQ times Q. So the only thing that goes to the other side would be affecting the coefficient MQ, and your new coefficient is going to be MQ minus M delta E KQ. Actually, I should use this so that this becomes plus. Okay. Now, if you look at it, then MQ is already given to you, and what is going to be 2 zeta omega n? Anyone has any? And how do you approach this? I want to see that how do you approach this. Let's discuss. Let's not rush through this. So the control law is given as negative KQQ, and I'm giving you that m delta E further, which was not a part of the stability derivatives, it's an input derivative. The feedback adds a term to the pitching moment equation. So what do you think we are supposed to do here?
So define a closed loop first.
Mm-hmm. And then?
And then take the determinant.
Okay.
And then,
Set it equal to the new.
yeah, and then solve for k.
Okay. So now, first of all, why I put this here as a single control law is, recall that I am not changing the natural frequency. The omega n square term will remain as it is. Okay. And then you will see that only the damping changes. But if you had a complete control law with alpha and q, you would change the natural frequency as well. So go ahead and investigate this on your own, that if you choose the only the first state, only the first element of the state as feedback, then what do you change? If you choose only the second element of the state as a feedback, then what do you change? And if you choose both of them, you are going to change both zeta and omega n. Okay, so here, since we only have like zeta, we are only looking at the q feedback term. What is going to happen is, you can go, so just because of the shortage of time, you will go ahead and note down the second q equation, and then for the second q equation, now you have negative m delta E times kq delta E, as the forcing term, which if you take it to the other side, it becomes mq plus m delta E times kq times q. So now what you are going to do is, what happened, where does mq appear in the A matrix, which means that the new closed loop matrix is going to be only MQ was affected by the state feedback law. So that is why I just need to go and update MQ. And now I'm going to do the same thing, and I'm going to find out the eigenvalues, which will give me the same omega n, but now I can set it to omega desired, which will give me the value for KQ. Is this clear to everyone? Yes.
So I don't really get the difference between open loop and closed loop.
Open loop and closed loop. Okay, I have 3 more minutes. I'll take that up right now. What's your question?
So you're only changing the reason why the only MQ is affected is because the control law that you gave is only a function of the Q gain.
Q gain, yes. Open loop and closed loop is basically, open loop as in, you are the pilot, you are looking at every sensor and you are correcting for every error. That's like, it's actually still feedback control. Open loop is like, you make an aircraft and you just shoot it into the air. No pilot, nothing.
Okay. So that's like the natural.
Yeah, exactly. The natural characteristics of the system, natural frequency, damping ratio, stuff like that. And that is why, because naturally nothing, like if things flew naturally as we wanted, then I would not have a job. And that is why we come up with stability augmentation systems. that it's not stable. Maybe it's fast, but it's not stable. So we need to add controls to it. We need to add a computer controller to it. We need to add a pilot to it. So that adds a closed loop. And how do you decide how much you want to control? You go ahead and look at and measure the current state values. Does that make sense? It's more of a control theory concept, to be honest. Like you can review modern control theory from. Did you guys take a controls class before? Yeah, state space and everything. So yep, you can go and review that. Okay. We are almost out of time, and I also have a class at 10 which I need to go to. So I will not do the long period mode right now. Watch the second half, and if I'll probably run out of time there as well, but I have the room until 5 p.m. So I'll keep the students here until 5 p.m. 4:30, whatever it is. If you want to come in the second half, you are welcome.